In this video, we're going to focus on how to calculate the actual yield, the theoretical yield, and the percent yield. So as you can see, the equation is on the board. Percent yield is equal to actual over theoretical times 100%. Now we're going to go over a few practice problems using that equation. We're also going to talk about the difference between the limiting reactant and the excess reactant, and how to find that as well. So let's go ahead and begin. Number 1, 32 grams of ethane C2H6 is placed in a container with 39 grams of oxygen gas. 28 grams of CO2 are collected at the end of the reaction. Identify the limiting reactant, calculate the percent yield, and determine the amount of excess reactant that remains. So, what's the first thing that you think that we should do in this problem? The first thing you need to do is write a balanced reaction. So we have ethane, C2H6, and it's going to react with oxygen gas. So this is a combustion reaction. And in a combustion reaction, the products are always carbon dioxide and water. So now, how can we balance this chemical reaction? Feel free to pause the video and balance it yourself, and then unpause the video to check the solutions. Now the first thing that you want to do whenever you're balancing a combustion reaction is balance the carbon atoms first. Notice that we have 2 carbon atoms on the left side. So we need to put 2 in front of CO2 on the right side. And notice that we have 6 hydrogens on the left. So we need to place a 3 in front of H2O. And so now let's balance the number of oxygens. We have 4 oxygens in 2 CO2s, 2 times 2 is 4, and we have 3 oxygens in 3 H2O. So to find a number that belongs here, you simply take the total on the right side and divide by the subscript. So basically, that's 7 divided by 2, or 7 halves. So you need about 3.5 in front of O2 to make it work. But now typically, when you have a balanced reaction, you want to avoid the use of fractions. You want to use whole numbers. So what we're going to do is we are going to multiply everything by 2. So this is going to change into a 2. 7 over 2 times 2 is basically 7. And this is going to be 4 and 6. So let me rewrite everything. So this is going to be 2, 4, 6, and 7. So you simply double everything at this point. So we have 4 carbon atoms on both sides, 12 hydrogen atoms, and a total of 14 on both sides. So we have 8 oxygen atoms here, plus 6, that equals 7 times 2, which is 14. So the equation is now balanced. So now that we have this balanced chemical equation, what do you think we should do next? So how can we identify the limiting reactant? And what is the difference between the limiting reactant and the excess reactant? The limiting reactant is the reactant that runs out first, and the excess reactant is going to be the one that's left over. So one of these 2 reactants is the limiting reactant, but how do we figure out which one? There's 2 different ways in which we can do it, but in this example we're going to go over one of those 2 ways. So what we need to do is find the moles of each reactant. So let's start with 32 grams of ethane, and let's convert it into moles. So to do that, whenever you want to go from grams to moles, you need to calculate the molar mass, and you can find that using the periodic table. In the periodic table, carbon has a molar mass of 12.01, and if you multiply that by 2, and if you add the 6 hydrogen atoms, each with a molar mass of 1.008, the molar mass of C2H6 is about 30.068 grams. So that's how many grams of ethane are found in 1 mole of C2H6. So 32 divided by 30.068, that's about 1.064 moles of ethane. So now let's do the same thing for the other reactant. So we have 39 grams of oxygen gas, and let's convert it to moles. So the molar mass for oxygen is 16, but because there's two atoms in this molecule, 16 times 2 is 32. So there are 32 grams per 1 mole of oxygen gas. And 39 divided by 32 is about 1.219 moles of oxygen. So which one is the limiting reactant? Is it O2 or is it C2H6? Now, just because we have a smaller quantity of moles of C2H6 doesn't mean it's the limiting reactant, because you need to take into account the coefficient of the balance reaction. So it's not the one that has the lowest number of moles that's the limiting reactant, but it's the one that has the lowest mole per coefficient ratio. So we're going to divide ethane by 2 because that's the coefficient for it in the balance reaction. And for oxygen, we are going to divide it by 7. And then we're going to see which of these numbers is smaller. So 1.064 divided by 2, that is about 0.532. And 1.219 divided by 7 is 0.174. So we can see that O2 has the lowest mole per coefficient ratio. So therefore, oxygen gas is the limiting reactant, which means that ethane is the excess reactant in this particular example. And so that's how you can identify the limiting reactant. Simply look for which one has which reactant that has the lowest mole per coefficient ratio. So now that we've identified the limiting reactant, we can now calculate the percent yield. But in order to find the percent yield, we need to calculate the theoretical yield. The theoretical yield is the maximum amount of grams that can form in this reaction, pretty much the maximum amount of product that you can obtain. So the product that we're concerned with is carbon dioxide. The amount of carbon dioxide that is actually collected in the experiment is the actual yield. So the 28 grams of CO2 that were actually collected, that is the actual yield for this problem. The theoretical yield is the maximum amount of grams of carbon dioxide that we can get in this reaction. So let's find out what the theoretical yield is. So since oxygen is the limiting reactant, let's start with 39 grams of O2. So we're going to do what is called a gram to gram conversion. And we're going to convert from the grams of one substance into the grams of another substance, in this case, grams of CO2. So let's convert grams into moles. So we already have the molar mass of O2. 1 mole of oxygen contains 32 grams of O2. So now, in order to convert from moles of O2 into moles of CO2, we need to use what is known as a molar ratio. So we wish to convert from O2 to CO2, so it's a 7:4 ratio. So what we need to put in the next fraction is we need to put 7 moles of O2 on the bottom and 4 moles of CO2 on the top. So what this means is that for every 7 moles of oxygen that are consumed in a reaction, 4 moles of CO2 or carbon dioxide are produced in this reaction. So notice that the grams of O2 cancel and the moles of O2 cancel as well. So now the last thing we need to do is convert moles into grams. So the molar mass for CO2, for carbon dioxide, if we add it, it's 12.01 for carbon, 16 for oxygen, but we have to multiply the 16 by 2. And so the molar mass of carbon dioxide is 44.01 grams per 1 mole. And so the units moles of CO2, they cancel. So now to get the answer, it's going to be 39 divided by 32 times 4 divided by 7 times 44.01. So the maximum amount of CO2 that can be produced in this reaction is about 30.65 grams of carbon dioxide. In a chemical reaction, the theoretical yield should be greater than the actual yield, because it's not practical to get a percent yield that's more than 100%. Something is wrong if that's the case. So now that we have the theoretical yield, we could find a percent yield. So this number, what it means is that this is the maximum amount of CO2 that we can get. So if all of the 39 grams of oxygen react, only 30.65 grams of carbon dioxide can be produced from it. So that's what it means. So now, in order to find the percent yield, we need to divide the actual yield, which is 28 grams, over the theoretical yield, which is 30.65, and we're going to multiply that by 100%. So you should get 91.35%. So that is the percent yield of this reaction. This is pretty good. So now, how can we find the percent error now that we have the percent yield? What equation can we use to get that answer? So let's make some space. The percent error equation is equal to, it's the absolute value of the difference between the theoretical yield minus the actual yield divided by the theoretical yield times 100%. So you can also see it as the experimental value, or the theoretical value minus the experimental value divided by the theoretical value. So that's how you can calculate percent error. So in this case, the theoretical yield is 30.65. Actually, I might need more space. So let's clear away this information. But remember the numbers that we have. So the theoretical yield is 30.65 minus the actual yield, which is 28, divided by the theoretical yield, which is also 30.65, and times 100%. So let's go ahead and calculate that number. So you should get, if you did this correctly, 8.65%. So that is the percent error. And keep in mind, the percent yield was 91.35%. That was the percent yield. Notice that the percent yield plus the percent error adds up to 100%. So if the percent yield is 80%, that means you have a 20% error. If your percent yield is 70%, the percent error is 30%. So once you have the percent yield, to find a percent error, simply subtract it by, or from 100. So 100% minus 91.35% will give you the percent error, which is 8.65. So I want to make sure that you understand that concept before we move on. But now you have the equation for percent error, so you can always use it if the need arises. So now let's focus on the third part of this problem. Let's determine the amount of excess reactant that remains. So let's clear away some stuff on this board. So feel free to pause the video and see if you can figure out how to calculate the amount of the excess reactant that remains. So let's begin. Here's the first thing you need to do. Start with the limiting reactant and convert it to the grams of the excess reactant. And then I'll explain what it means. So there are 32 grams of oxygen gas, and we're going to convert it to moles. So we know that 1 molar of oxygen has a mass of 32 grams. And so the units, grams of O2, cancel. And so next we're going to use the molar ratio. We're going to convert to the moles of the other reactant, C2H6. So as you can see, it's a 7:2 ratio. So for every 7 moles of oxygen that reacts, 2 moles of ethane, C2H6, reacts with it as well. Now the last thing that we need to do is convert moles of C2H6 into grams. And we already have the molar mass. It's 2 times 12.01 plus 6 times 1.008. And so the molar mass is about 30.068 grams per 1 mole. So 32, that should be a 39 actually. I don't know why I have 32, but this is a 39 because we have 39 grams of oxygen. So 39 divided by 32 times 2 divided by 7 times 30.068. And so this is equal to 10.47 grams of C2H6. Now you might be wondering, okay, so what does this number even mean? So what this means is that 39 grams of O2 reacts with 10.47 grams of ethane, C2H6. Now we know that because the oxygen is the limiting reactant, the entire 39 grams of oxygen is going to react. So that means out of the 32 grams of C2H6 that we have, only 10.47 grams reacts with the 39 grams of oxygen gas. So the amount that's left over is the difference between the total amount of ethane that we have and the amount that actually reacts. So if you want to find out how much ethane reacts, your answer is 10.47. If you want to find out how many grams of the excess reactant that remains after the reaction, you have to subtract. So 32 minus 10.47 is going to give you the answer. So the amount of excess reactant that remains is 21.53 grams of C2H6. Number 2, 23 grams of ethanol C2H5OH is placed in a container with 41 grams of oxygen gas. If the reaction is 85% efficient at a certain temperature, how many grams of CO2 do you expect to collect in this reaction? And how many grams of the excess reactant actually reacts? And how much remains? So feel free to pause the video and try this problem yourself. So what's the first thing that we should do? So let's go ahead and balance the reaction. So we have C2H5OH, and it's going to react with oxygen gas. And it's a combustion reaction like the other one, so we're going to get carbon dioxide and water as a product. So let's balance this reaction. We have 2 carbon atoms on the left side, so we need to put a 2 in front of CO2. Whenever you're balancing a combustion reaction, always balance the carbon atoms first, and then the hydrogen atoms second, and then balance the oxygen atoms at the very end. So notice that we have 6 hydrogen atoms on the left. 5 plus 1 is 6. And we have 2 on the right. 6 divided by 2 is 3, so we need to put a 3 in front of H2O. Now notice that we have 7 oxygens on the right side. 3 from H2O and 4 from CO2. But we have 1 from ethanol. So 7 minus 1 is 6. 6 divided by 2 is 3. So we need a 3 in front of O2. So we have 2 carbon atoms on both sides, 6 hydrogen atoms on both sides, and a total of 7 oxygen atoms on each side. So now the reaction is balanced. So the next thing we need to do at this point is identify the limiting reactant. But we're going to do it differently than the way we did it in the first example. So in order to find the amount of grams that we expect to collect in this reaction, which is basically the actual yield, we need to first find the theoretical yield. So what we're going to do is we're going to convert the grams of each reactant into the grams of product. And whichever reactant gives us a small amount of the grams of CO2, that reactant is going to be the limiting reactant. So that's the second way, or another way in which you can find the limiting reactant. Let's start with the 23 grams of ethanol, C2H5OH. Let's convert it to moles. So carbon has a molar mass of 12.01 times 2 plus the 6 hydrogen atoms, each with a molar mass of 1.008 plus 16 for oxygen. So the molar mass that you should have for ethanol is about 46.068 grams per 1 mole. Now the next thing we need to do is convert moles of ethanol into moles of the product CO2. And as we can see, it's a 1:2 ratio. So for every 1 mole of C2H5OH that reacts, 2 moles of CO2 are produced. And now at this point, we can convert this to get the grams of CO2. So for every 1 mole of CO2, there are 44.01 grams. And we have this molar mass from before. We calculated already. It's 12.01 plus 2 times 16. So the units grams of ethanol cancel, and moles of ethanol cancel, and moles of CO2 cancel as well. And so if we type this in, it's going to be 23 divided by 46.068 times 2 times 44.01. So we're going to get 43.95 grams of carbon dioxide, CO2. So what this means is that if all of the 23 grams of ethanol reacts, we can get a maximum of 43.95 grams of CO2. And so that's what it means. It's simply a relationship between the reactant and the product. It's a quantitative relationship. So now let's calculate the quantitative or the stoichiometric relationship between the grams of oxygen gas and carbon dioxide. So let's start with 41 grams of O2. Let's convert it to moles. And now let's use the molar ratio so that we can convert from the moles of O2 to the moles of CO2. And as we can see, it's a 3:2 ratio. So for every 3 moles of O2 that reacts, 2 moles of CO2 are produced. And then the last part is going to be the same. We just need to convert moles of CO2 into grams. And so the molar mass is going to remain 44.01 grams. So grams of O2 cancel, moles of O2 will cancel as well, and the same is true for the moles of CO2. So it's going to be 41 divided by 32 times 2 divided by 3 times 44.01. So we're going to get 37.59 grams of CO2. So now what this means is that if all of the 41 grams of O2 reacts, then we can get a maximum of 37.5 grams of CO2. Now we have 2 different potential theoretical yields, 43.95 and 37.5. Which one is the correct answer? The correct answer is the smaller of the 2 numbers. So the theoretical yield is 37.5. Because once you have 37.5 grams of CO2 produced, that means all of the grams of oxygen reacts. So if there's no more oxygen in the reaction chamber, then ethanol cannot react anymore. So we're never going to get to 43.95 because once we get to 37.5, that's it. Oxygen is out. There's no more oxygen left to react. And so the remaining amount of ethanol, it can't react with anything, so we're never going to get to 43.95. So therefore, the theoretical yield for this reaction is 37.5 grams. And the limiting reactant is the reactant that gave you the smaller theoretical yield. So therefore, we know that O2 is the limiting reactant, and the one that gave us a larger theoretical yield is the excess reactant, which is ethanol. So that's another way in which you can find the limiting reactant. Convert the grams of each reactant into the grams of product, and whichever reactant gives you the smaller amount of product or the smaller theoretical yield, that's going to be the right theoretical yield, and the reaction that gave you that theoretical yield is the limiting reactant. So sometimes it might be faster to do it this way if you have to find the theoretical yield anyway. Okay, so now let's continue. Now that we have the theoretical yield, which we said was 37.59 grams of carbon dioxide, how can we calculate the actual yield? So if the reaction is 85% efficient, how many grams of CO2 do you expect to collect in this reaction? All you need to do to find the actual yield is find 85% of 37.59. So it's just 37.59 times 0.85. So 85% of that number is about 31.95. So that's how many grams of CO2 that we should expect to collect on a practical basis, because most reactions are not 100% efficient. So if it's 85% efficient, that's pretty good. We won't get the maximum amount of CO2 that we can collect in this reaction. So we're going to get 31.95. So that's the actual yield. Now, I know some of you out there prefer to use an equation to get the actual yield. So let's start with this equation. Percent yield is equal to the actual yield divided by the theoretical yield times 100%. So if we divide both sides by 100%, we're going to get the percent yield, but in a decimal form. And we also need to multiply by the theoretical yield, both sides, so that t will cancel on this side. So on the right side, the 100 cancels and the t cancels, so we only have the actual yield on the right side. So the actual yield is equal to the theoretical yield times the percent yield, but when the percent yield is divided by 100%. And basically that's what we did, if you think about it. So we plugged in the theoretical yield, which was 37.59, and we plugged in the percent yield, which was 85%, but we divided it by 100%, so we changed it to a decimal, and this gave us the actual yield. 85 divided by 100 is 0.85, so we did 0.85 times 37.59, and basically that's the same thing as what we did here, and so that gave us the answer. So whenever you want to find the actual yield, it's equal to the theoretical yield times the percent yield, but divided by 100, or 100%. That's how you calculate the actual yield. Now, let's find out how many grams of excess reactant that actually reacts in this reaction. So let's start with the limiting reactant, which is 41 grams of oxygen gas. Let's convert it to moles. So 1 mole of O2 contains 32 grams. And let's convert that into the moles of the reactant, or the excess reactant. So we know we need to use the molar ratio. It's a 3-to-1 ratio. So for every 3 moles of O2 that reacts, 1 mole of ethanol, C2H5OH, reacts with it. So now we got to convert that to grams. So the molar mass of ethanol was about, if I remember correctly, 46.068 grams, which we had in the last example. So 41 divided by 32 times 46.068 divided by 3, you should get 19.67 grams of C2H5OH. So this is the quantity of ethanol that reacts with the 41 grams of O2. So this is the amount that actually reacts or participates in a reaction. So 41 grams of O2 reacts with 19.6 grams of ethanol. So the amount that remains is a difference between 23 and this number. So 23 minus 19.67, which is basically 3.33 grams. That's the amount of the excess reactant that remains after the reaction is complete. So that is it for this video. I hope that you understand the concept of the limiting reactant and the excess reactant, and how to find out how much excess reactant remains. So thanks for watching, and have a great day.